Today we are going to learn about implementing load balancing in cloud environments. You will discover practical steps to deploy and configure load balancers on major cloud platforms, enhancing your skills and ensuring high availability and reliability of cloud applications. Welcome to our exploration of implementing load balancing in cloud environments. Load balancing is a key component in cloud computing, designed to distribute incoming network traffic across multiple servers. This ensures that no single server becomes overwhelmed, maintaining high availability and reliability. As cloud computing continues to grow, understanding and implementing efficient load balancing is essential for optimizing resource utilization and ensuring seamless user experiences. Whether you're managing a small application or a large-scale infrastructure, mastering load balancing is crucial for modern cloud environments. Cloud load balancing is a service that helps distribute network traffic across several servers, ensuring no single server becomes a bottleneck. There are several types of load balancers, including hardware, software, and cloud-based solutions. Cloud load balancers, offered by major providers like AWS, Google Cloud, and Azure, automatically distribute incoming application traffic across multiple targets, such as Amazon EC2 instances, IP addresses, and containers. They provide high availability and fault tolerance, improve application performance, and reduce costs by optimizing resource usage. The challenges of implementing cloud load balancing include configuring accurate traffic distribution policies and dealing with the dynamic nature of cloud environments. Solutions include using intelligent algorithms that adapt to traffic changes and integrating load balancers with monitoring tools to detect anomalies and adjust configurations in real time. AWS offers Elastic Load Balancing, ELB, as part of its suite of cloud services, providing three types of load balancers: Application Load Balancer, ALB, Network Load Balancer, NLB, and Gateway Load Balancer. Each type serves different needs, with ALB being ideal for HTTP/HTTPS traffic and microservices, NLB for ultra-low latency connections, and Gateway Load Balancer for deploying and managing a fleet of third-party appliances. To set up an ALB, you first configure listeners, which are channels for incoming connections, and target groups, which are destinations for these connections. Security is paramount, so it's crucial to configure SSL termination for encrypted traffic and set up appropriate security groups. Monitoring with AWS CloudWatch provides insights into performance and helps in proactive management of your load balancers.
Google Cloud Load Balancing offers both global and regional load balancing options, catering to diverse needs. It supports external and internal TPS load balancing, capsule proxy load balancing, and internal pipe load balancing. Global load balancing allows traffic distribution across multiple regions for high availability, while regional load balancing is confined to a specific region. Configuring Google Cloud Load Balancers involves setting up backend services, which define how traffic is routed to the application instances. Advanced traffic management capabilities, such as setting up all maps and enabling session affinity, optimize the distribution of requests. Google Cloud Monitoring, integrated with load balancers, provides real-time insights into traffic patterns and helps in making data-driven decisions for scaling and optimizing resources.
Azure offers several types of load balancers, including Azure Load Balancer for Layer 4 traffic and Application Gateway for Layer 7 traffic. The Azure Load Balancer provides high availability for your applications by distributing incoming traffic among healthy instances in cloud services or virtual machines. To set up a public load balancer, you need to configure front-end IP, back-end pools, and load balancing rules to determine how traffic is distributed. Health probes are essential for monitoring the status of application instances and ensuring traffic is only directed to healthy instances. Network Address Translation, NAT, rules can be configured for port forwarding scenarios. Azure Monitor offers comprehensive tracking and insights, helping you maintain optimal performance and quickly react to any issues.
Scaling is a critical aspect of cloud computing, ensuring applications can handle varying workloads effectively. Load balancers are integral to this process, working hand-in-hand with auto-scaling to dynamically adjust the number of resources based on demand. This elasticity is crucial for maintaining application reliability and performance, allowing cloud services to efficiently respond to traffic spikes and minimize costs during low demand periods. By integrating load balancers with auto-scaling policies, you ensure that your application infrastructure grows or shrinks in response to real-time conditions, optimizing resource allocation while maintaining consistent user experience and avoiding over-provisioning.
Security is a paramount concern in cloud load balancing. Ensuring the endpoints of your load balancers are secure is the first step, achieved through robust access control lists, ACLs, and firewalls. Implementing SSL/TLS encryption is critical for protecting data in transit, safeguarding user interactions with web applications. Authentication mechanisms and secure API gateways further enhance security by controlling who can access your services. DDoS protection strategies should be in place to defend against volume-based attacks that can disrupt service availability. Following best practices, such as regular security audits and updates, helps maintain a secure environment, ensuring your applications remain resilient against evolving threats. Monitoring and analyzing traffic is crucial for maintaining efficient load balancing operations. Understanding traffic patterns allows you to optimize resource allocation and improve user experiences. Tools like AWS CloudWatch, Google Cloud Monitoring, and Azure Monitor provide insights into traffic flows, helping you interpret and act on data trends. By regularly analyzing traffic, you can detect anomalies, anticipate potential issues, and implement proactive resolutions before they affect service availability. Continuous monitoring also supports performance optimization efforts, ensuring your cloud environments operate efficiently and effectively, meeting the demands of your users.
Cost optimization is a key consideration in cloud load balancing, balancing performance with budget constraints. Selecting cost-effective load balancers and right-sizing resources are primary strategies. By optimizing resource allocation, you can avoid unnecessary expenses, ensuring that you're only paying for what you need. Implementing auto-scaling policies allows for dynamic adjustments in resource usage, aligning costs with current demands. Regular monitoring of usage patterns and adjusting plans based on real-time data helps further optimize costs. These strategies ensure that your cloud operations remain economically viable while maintaining high performance and reliability.
In conclusion, load balancing is an essential component in cloud environments, crucial for maintaining high availability, reliability, and performance. We've explored the configuration of load balancers on major platforms like AWS, Google Cloud, and Azure, offering practical steps and insights. As you continue to work with cloud technologies, remember the importance of continuous learning and adaptation, applying the strategies and best practices discussed to optimize your cloud operations. The skills gained here are invaluable in navigating the dynamic and ever-evolving landscape of cloud computing, empowering you to deliver robust and efficient solutions.